Hello students, so continuing our lectures on numerical analysis, we will first start with trapezoidal rule today. So if you have a function like this as given here and you have been asked to find out this integral, so what you do, you will form a trapezoid from the two limits. So if a and b are the two limits, so you will draw a trapezoid like this, and the area here is approximately equal to the integration that you would like to find out. Now, so this value is actually equal to the area of the trapezoid that we have formed, and using the basic formula of the area of a trapezoid, it comes out to be b minus a by 2 into fa plus fb. Now, as you can see that this is not very accurate. So to make it more accurate, what we need to do, we need to apply a higher order polynomial into the value of fx, so that it can match with what has been provided. And if you do that, the accuracy actually rises up. And so we can have more accurate values of a. Whatever may be the accuracy, the basic form of the equation will be like this. That means fx we will be c1 f1a or c2 fp. This will be the form of the final equation. We have already discussed one-point Gauss quadrature rule in our first class. Now there is a second point Gauss quadrature rule also that we would like to discuss here. So this is the trapezoidal rule that we recently discussed. Now what we will do in a two-point Gauss quadrature rule is that we will first assume that we will take a third order polynomial. As you can see, we assume that fx is equal to a third order polynomial, and if we put the values of this fx into the equation, and we just simplify, then we come up with this expression. Now, from Gauss quadrature rule, what we also do is we assume that this fx is equal to c1 f1 x1 plus c2 f2 x2, as you can see written here, where x1 and x2 are two values of x which fall between the limits a and b. If you compare this value, by using this, we actually get the values of, we get another expression involving a and c1. So if you compare these two expressions, we get these values, and on finding out the solution of these values, you get the following simultaneous nonlinear equations, where c1 is b1 by a by 2, c2 is also b1 by a by 2. We have different values of x1 and x2. Now, in a 3-point, this goes for a 2-point Gauss quadrature rule. For a 3-point Gauss quadrature rule, again, we have to take an fifth order polynomial, and there will be 6 unknowns. So as we keep on increasing the order, the number of unknowns and the number of polynomial also increases. And for an n-point n-point Gauss quadrature rule, there will be 2n unknowns and 2n minus 1 to the power n polynomial. So if you take the example, suppose you would like to find out the value of this integrand. So we use the values obtained from, this will be plus, b plus a. So we put the values obtained from our expressions. So we can easily find out the value of this expression, and this comes out to be equal to 0.89. So this is all about Gauss Quadrature rule. Let us start with another aspect of numerical analysis, that is solving differential equations. Now, basically, for ordinary differential equation solution by numerical analysis, we follow two methods. One is called the Euler's method, and the other one is called method. So we'll discuss Euler's method here now. In Euler's method, what happens is that it is not coming straight. You need to do that a little bit. So in Euler's method of finding out the solution of a differential equation, suppose we have a very basic differential equation like this, and one boundary value condition is given. So if we go into the plot, so if this is the equation fxy, then we need to find out the solution, and this is the boundary condition that y at x is equal to 0. So what we do here, we actually find out the slope. We take initialize 2 points. One is xi and another one is xi plus 1, and we draw a slope here. So let the angle is phi. So the slope tan phi turns out to be yi plus 1 minus 1 by xi plus 1 minus xi. So this is the slope value, and so again, if we continue, then fxi is actually the slope, and so this is the value that we obtained for the expression of Euler's method for differential equation and differential equation analysis. And this h is basically the step size, and the difference between the 2 points that we have chosen. Okay, now as we increase or decrease the step size, the error also decreases, and we move towards accuracy. Let's take an example. Suppose let's take another page. Suppose this is the equation that we need to solve. dy by dx is equal to plus 0.4y is equal to 3 e to the power minus x, and this is the boundary condition. So we initially start with age is equal to 3. Now how to find out the value of age is equal to 3? We take an initial guess that age is equal to 3, considering the nature of the function. So we put the value of h is equal to 3. This is what we obtain, and this is the basic equation of Euler's rule. So the next step goes like this. So for the first iteration, for I is equal to mean, this is the iteration value. This is the iteration. So the first iteration, we have taken the value of y is equal to 3. So the value of y comes out to be 8. Now the true value of y is 2.7. So you can see there is a huge amount of error involved. Now to reduce this error, what we need to do? We need to reduce the value of 8. So initially, this was 0 and this was 3. So there has been a huge error by taking 3. So we take the half of this, that is, we take as 1.5. So taking 1.5, you can see that since the true value was 2.7, so by taking 1.5, we see that we see that the value, the error, this is the value y2, so it has come close to this value. So it shows that as we reduce the value of h, the error also reduces.